Hello students, in today's lecture I will discuss the differential vector identities which are required to be used in electrostatics and magnetostatics. Fourth identity is vector del r raised to n equal to n r raised to n minus 2 into vector r. Here vector r is a position vector and r is its magnitude. So now to prove this, we start with the left hand side, which is the grade of r raised to n, that is vector del r raised to n. Now here the r is equal to x square plus y square plus z square raised to half. So therefore r raised to n equal to x square plus y square plus z square raised to n by 2. So we find now the vector del of this bracket, which is x square plus y square plus z square raised to n by 2. This vector del of this is a scalar function. So it is called as the grade of this scalar function, which is x square plus y square plus z square raised to n by 2. We use the formula for the gradient, which is dou by dou x of that scalar function into I cap plus dou by dou y of this scalar function into j cap plus dou by dou z of that scalar function into k cap. Now let us try to evaluate this first term. The first term is partial derivative of the scalar function with respect to x into I cap. Now that I cap comes as a multiple. Now when you differentiate this partially with respect to x, you are differentiating a bracket raised to power. So when you find the derivative with respect to x partially, that power comes as a multiple. So this n by 2 comes as a multiple and the power reduces by 1. So this n minus 2 minus 1 into derivative of what is there inside the bracket. And we are finding the derivative with respect to partially with respect to x. What is there inside the bracket? So derivative of x square with respect to x partially is 2x and the derivative of y square with respect to x partially is 0 because y is constant and z is also constant, only y is variable. And third is partial derivative of z square with respect to x, that is also 0. So it results into this first term. Similarly, in the second term, you are finding the partial derivative with respect to y. So it is to be differentiated similar to the first term. But here, in the when you differentiate inside the bracket, so derivative of y square will become 2y, whereas derivative of x square and z square, that is 0. In same way, in the third term, it is a partial derivative with respect to z. So when you differentiate partially inside the bracket with respect to z, so partial derivative of x square and partial derivative of y square with respect to z is 0, whereas partial derivative of z square with respect to z is 2z. Then this 2 in the numerator and 2 in the denominator, in each of the term they cancel. And this n is a common to all these three terms. Then x square plus y square plus z square raised to n by 2 minus 1 is also common, and this n by 2 minus 1 is written as n minus 2 by 2, and what remains inside is x I cap plus y j cap plus z k cap, and this is nothing but vector r. This x I cap plus y j cap plus z k cap is vector r, and this x square plus y square plus z square raised to half is r. So it is r raised to n minus 2, and this n comes as a multiple. So this is nothing but the right hand side. The fifth identity is del square r raised to n equal to n into n plus 1 r raised to n minus 2. Now del square r raised to n means a Laplacian of this scalar function r raised to n. and we have to prove that equal to n into n plus 1 r raised to n minus 2. So let us start with the left hand side, which is del square r raised to n. As we have used in the previous identity, that r raised to n is x square plus y square plus z square raised to n by 2. And by using the definition for the Laplacian, we write the dou 2 by dou x2 of that scalar function plus dou 2 by dou y2 of that scalar function plus dou 2 by dou z2 of that scalar function. Now this dou 2 by dou x2 means differentiating partially twice successively. So what we do here is, first we differentiate once, again we differentiate that. So this dou 2 by dou x2 can be written as dou by dou x and dou by dou x of that scalar function, plus that dou 2 by dou y2 can be written as dou by dou y of dou by dou y of that scalar function, plus dou 2 by dou z2 can be written as dou by dou z into of dou by dou z of that scalar function. So let us now consider the first term, and first we'll differentiate the scalar function with respect to x partially. So when you differentiate this term partially, that n by 2 comes as a multiple and that power reduces by 1, so it becomes n by 2 minus 1. Then partially differentiate what is there inside the bracket, and when you do that, the partial derivative of x square with respect to x is 2x. The partial derivative of y square is 0 with respect to x, and partial derivative of z square with respect to x is 0. In same way, in the second term, we are differentiating partially with respect to y. So derivative of that x square is 0, z square is 0, whereas derivative of y square is 2y. In same way, in the third term, this partial derivative with respect to z of this, what is there inside the bracket, that partial derivative of x square with respect to z is 0, partial derivative of y square with respect to z is 0, but partial derivative of z square with respect to z is 2z. Then in each term, this 2 in the numerator and 2 in the denominator cancels. Now we want to differentiate this partially, first term with respect to x, second term with respect to y, third term with respect to z. Now here there are two functions, x square plus y square plus z square is to n by 2 minus 1, one function, other function is x. So when you differentiate partially with respect to x, we find a derivative of the product. So we use the formula that uv dash equal to uv dash plus u dash v, or u dash v plus uv dash. So that formula we will use it for each of the term. Now here we have to do the partial differentiation in the first term with respect to x, in second term with respect to y, in third term with respect to z of the product of these two functions. These two functions are x square plus y square plus z square raised to n by 2 minus 1, and second function is x. So we use the derivative of the product formula, which is u dash v plus uv dash. So therefore here in the derivative with respect to x partially of this part is n comes as a multiple, then derivative of this function, so n minus by 2 minus 1 comes as a multiple, then that power reduces by 1 to become n by 2 minus 2 into derivative of what is there inside the bracket, that is 2x, into a second term, plus the first term is this n into x square plus y square plus z square is to n by 2 minus 1 into derivative of second term partially with respect to x, so it becomes 1. Same way, this part, the product of these two functions, are differentiated partially with respect to y to get this quantity. Then similarly, this third term, which is a product of the two functions, and we are differentiating partially with respect to z, you get this one. Now, in this first part of these three terms, n into n minus 2, because 2 and this 2 cancel, so it becomes n minus 2, comes as a common, and what remains inside is x square plus y square plus z square raised to n by 2 minus 2, which is written as n minus 2 by 2. Now this second term of each of these, they are equal, so it becomes thrice. So thrice n into this x square plus y square plus z square raised to n by 2 minus 1 is written as n minus 2 divided by 2. In the next step, this n into n minus 2 comes common, this 3n comes common, and what remains outside, that is x square plus y square plus z square raised to n minus 2 by 2, can be written as r raised to n minus 2. And then open this bracket, n into n square, then n into 2, that is minus 2n, and this is 3n, and this minus 2n plus 3n is 1n. So now from that n comes out, and what remains inside is n plus 1 r raised to n minus 2, and which is equal to right hand side. The sixth identity is del of 1 by r equal to minus vector r divided by r cube equal to minus unit vector r divided by r square. So let us start with the left hand side, which is del of 1 by r, which means it is grade of 1 by r. So we write here 1 by r as r raised to minus 1, and then we use the formula for grade of r raised to minus 1, which is dou by dou x of r raised to minus 1, which is x square plus y square plus z square raised to minus half into I cap plus dou by dou y into x square plus y square plus z square raised to minus half j cap plus dou by dou z of x square plus y square plus z square raised to minus half k cap. Now let us differentiate the first term partially with respect to x. So when differentiated partially with the x, that power comes as a multiple, which is minus half, and the power reduces by 1, so minus half minus 1, that is minus a by 2, into the partial derivative with respect to x of what is there inside a bracket. And when that is differentiated, the partial derivative of x square with respect to x is 2x, and partial derivative of y square plus z square with respect to x is 0 into I cap. In same way, we can differentiate second term partially with respect to y and differentiate third term with respect to z. Then in each term, 2 in the numerator cancels with the 2 in the denominator, and this x square plus y square plus z square raised to minus 3 by 2, which is r raised to minus 3 with minus sign, comes out as a common, and what remains inside is xi cap plus yj cap plus z k cap. This minus r raised to minus 3 comes down in the denominator as r raised to 3, and what is there in the bracket xi cap plus yj cap plus zk cap is the position vector, vector r. The position vector divided by magnitude of the position vector, that is vector r divided by r, is r cap, and what remains in the denominator is r square, and that is equal to right hand side.